Imagine this for a second. You look up at the night sky and, really know that somewhere out there, there's another Earth, another world, maybe even with life, just waiting. It's something everyone thinks about, right? That search for our cosmic neighbor. So today we're going to dig into how NASA is, actually planning to make that happen. We're focusing on their roadmap for exploring exoplanets, specifically 17 high-priority science goals that their Exoplanet Exploration Program, or XIP, has laid out. And this isn't just wishful thinking. This roadmap is really detailed. It's in Rev Age of XIP's tactical plan that was circulated internally back in January 2025, and it builds right on the big recommendations for the 2020 Decadal Survey.
Yeah.
So our mission here really is to give you a kind of shortcut, a primer on the knowledge gaps NASA really needs to close in the next, say, 3 to 5 years. It's all about the groundwork, what has to happen before we can even seriously talk about characterizing other Earths. Okay, so let's set the scene. The big long-term goal for NASA, the thing driving a lot of this, is this incredible future mission, the Habitable Worlds Observatory, HWO.
Right.
It sounds really ambitious. It's kind of a merger of two older concepts, wasn't it? LVOR and HABEX.
That's exactly right. HWO is it's a huge undertaking, and it has this very specific, very bold goal. Actually, it characterizes 25 potentially habitable exoplanets during its mission.
25?
Yeah, and this is the key thing, there's a lot of what we call precursor science that needs doing before HWO even gets off the ground.
Precursor science.
And we need to make sure its design, how it plans its surveys, everything is based on what space is really like, astrophysically speaking, not just our, best guesses or models.
Okay, that makes sense. So to make HWO actually work, we need some fundamentals sorted out first. What are those sort of foundational things we need to pin down?
Precisely. NASA's focusing on a couple of key precursor gaps right now. First off, there's gap number 5, estimating the occurrence rates of temperate rocky planets.
Occurrence rates.
Yeah.
So how common these Earth-like planets actually are.
Exactly. Knowing how common or how rare they are is just fundamental. It changes how you design the mission, how long it needs to observe, everything. If they're super rare, well, that's a very different challenge.
Okay, that's number 5. What else?
Then there's gap number 6, assessing detection yield across telescope architectures. So you take those occurrence rates from gap 5,
right,
and you figure out, okay, with this telescope design, how many planets could we realistically expect HWO to find? If we get those yield estimates wrong because our occurrence rates were off, or our understanding of the telescope performance is optimistic,
the whole mission could underdeliver.
It could fundamentally jeopardize the yield. Yeah, it's not just a minor error.
Wow. Okay, here's something that sounds maybe less obvious.
Yeah.
How does something like, dust in space fit into finding these tiny planets light years away?
Dust. Yeah, it sounds minor, but it's actually a huge deal. That brings us to gap number 11, exozodiacal dust distributions.
Exozodiacal. So dust around other stars.
Exactly. Think of it like leftover debris from asteroids bumping into each other, or from comets, all orbiting the star we're trying to look at. It creates this faint haze.
A cosmic fog.
Kind of, yeah. And if there's enough of it, this dust, this cosmic grate, it can totally swamp the incredibly faint light coming from the planet itself.
So it blinds the telescope almost.
It can, yeah. It directly messes with the accuracy of those yield estimates we just talked about. So we really need to nail down how much dust is typically out there around different types of stars.
Right.
Getting these dust studies right makes sure HWO's design is, robust against the actual conditions it's going to face. We don't want expensive surprises later.
It's pretty amazing the level of detail needed just to prepare for the mission. So, okay, let's say HWO is built, it's launched, it's working. Its main job is spectroscopy of small exoplanet atmospheres. That sounds incredibly difficult.
Oh, it is. It's a massive challenge.
But what groundwork do we need for that part?
Right. So that main objective, that's gap number 1, spectroscopic characterization of small exoplanet atmospheres. That's the ultimate goal for HWO.
Okay.
But to get there, we need gap number 2, developing atmospheric models. We need really, really good computer models that can predict what an atmosphere with certain gases should look like.
Like what its spectrum should show.
Exactly.
Yeah.
There are efforts like the Exoplanet Opacity Database, which is working on improving molecular line lists. Think of those as unique fingerprints for different molecules.
Barcodes.
Yeah, like barcodes. They show exactly how much light each molecule absorbs or lets through at different wavelengths. The big question is, how good will our predictive models be when HWO sends back real data?
We need to trust the models to interpret the observations.
Precisely.
Yeah.
And then there's gap number 13, improving spectrographic reference data. This means doing really careful measurements down here in labs on Earth.
Lab work. How does that help a space telescope?
Well, we need to measure the exact absorption features of atoms and molecules under controlled conditions. These lab measurements are vital. Without them, HWO would be like having, I don't know, a super powerful camera, but no idea how the colors are supposed to look.
Okay. Calibration.
Exactly. It's about calibrating HWO's instruments so we can accurately figure out what gases are in that atmosphere, minimizing the guesswork when we get that precious light back, making sure we read the message correctly.
That's a ton of prep work just to get the data and be ready to analyze it. So once we actually have that spectrum, that barcode, how do we interpret it fully? Does it matter where the planet came from or what its star is like?
Oh, absolutely it matters. You can't really interpret the atmosphere in isolation. That leads us to gap number 3, deriving physical parameters of exoplanets.
Physical parameters.
Yeah.
Like size and mass.
Right. Mass, radius, temperature, things like recent ground-based high-contrast imaging challenges. These are techniques trying to block the star's glare to see the planet directly.
Yeah, I've heard of those.
They're helping us get better at figuring out these basic properties from very limited data. Knowing if it's a big rocky planet or a small gassy one is, well, kind of important for habitability.
Makes sense. What about the star itself?
Crucial. That's gap number 7, characterizing host star environments. Things like the star's metallicity.
Which is like its chemical composition, how much heavy stuff it has.
Exactly. Also, its activity cycles, does it have big flares, and its history of UV radiation. All of that deeply affects how planets form around it and how their atmospheres change over cosmic time.
So the star's life story shapes the planet's potential for life.
In a big way. So the question becomes, how do these improved ways of measuring star properties change our ideas about habitability, especially around stars very different from our sun? It's all tangled together, the star, the planet, the atmosphere.
Okay, it's clear these are really significant challenges. But switching gears a bit, what's NASA actually doing about these gaps now? Are there things already happening?
Oh, absolutely. Yeah, the exit report isn't just a list of problems. That's important. It actually maps out ongoing initiatives that are tackling each specific gap.
Okay, like what?
Well, we mentioned the exoplanet opacity database that's directly addressing gap number 2, standardizing those molecular line lists, those barcodes.
Right.
And for gap number 3, figuring out planet parameters, there are these community data analysis challenges. NASA and others run competitions using real or simulated high-contrast imaging data. It gets lots of smart people working on refining the analysis techniques.
That's pretty cool, using the whole community's brain power.
Exactly. It's a great model.
And that really connects back to you, the listener. If you're interested, if you have the skills, these kinds of platforms are ways people can actually get involved and contribute right now.
Yeah.
But okay, even with a good plan and smart people, there are always hurdles. What about the practical stuff? Funding, people.
Yeah, that's the elephant in the room right now, unfortunately.
Uh-huh.
There was a proposed pretty significant budget cut, something like 47% for the Science Mission Directorate. That throws a lot of uncertainty onto ExoP's timeline for all this precursor work.
A 47% cut, that's huge.
It is. Now, the good news is the lead authors of this report, Drs. Carl Stapelfeld and Eric Mamajek, they're still involved, providing continuity. But NASA has also had people leave under a deferred resignation program, which, puts more pressure on the remaining team.
So less money and potentially fewer people.
Right. And the impact is that these funding pressures could really slow down the technology development needed, delay these crucial precursor studies. It basically turns it into a race against time for NASA to get this groundwork done before the main HWO development needs to kick into high gear.
Okay, so given those constraints, the budget worries, the staffing, what does that mean for keeping the momentum going, for actually reaching this big goal? So pulling it all together, what we've seen in this deep dive is that NASA has this really systematic plan. They've identified these 17 key knowledge gaps, and they're working to close them over the next few years. It's all about laying that absolutely essential foundation for the Habitable Worlds Observatory, so it can actually do its transformative work, characterizing potentially Earth-like planets.
And every step forward, whether it's getting those occurrence rates more precise or doing that painstaking lab spectroscopy, each step builds confidence that we can actually detect and understand these distant worlds.
Yeah.
And what this report really does, I think, is it brings the whole exoplanet community together around a clear set of priorities. Everyone knows what Scylla needs doing. It gives focus.
A shared roadmap.
Exactly. It's not just a random list of science questions. It's a strategy, a blueprint for potentially, the biggest discovery ever.
And as we think about all the incredible science, all the technology, that question from the source material really hits home, doesn't it?
Yeah.
It's something for you to really chew on. Are we ready, scientifically, maybe even culturally, to find our first truly habitable world?
It's a profound question.
It really is. Not just about the finding, but what comes after. What it means for us. Something to think about.